In this episode, we will have a look at the first level of Protostar from exploitexercises.com. If you have questions about the setup, you can watch the previous video. Generally, I advise you to stop the video right here and work on it by yourself. Maybe give it a day and see how much you can figure out. And after that, watch my explanation. But if you feel completely lost, then just follow me. This here should give you enough information to solve the next level on your own. So let's first have a look at the challenge description. This level introduces the concept that memory can be accessed outside of its allocated region, how the stack variables are laid out, and that modifying outside of the allocated memory can modify program execution. And this level is located at op protostar bin stack 0. Okay, next we will have a look at the source code which is provided below. Let's start with the first quick overview. This is clearly a program written in Z. It reads some input with gets, then checks the modified variables and prints either success or fail message. So obviously, the goal of this level is to make the program print the success string. Note, this level is not about executing arbitrary code to gain root privileges. First we have to understand a couple of basics. A real full root exploit will come in later levels, so for now let's just focus on smaller goal. We can also execute the stack 0 program, and we can see that it seems to wait for some input and then prints try again. Okay, so let's have a more detailed look at the code. There are two local variables, an integer number modified and a char array buffer with space for 64 characters. An array of chars in C is basically just a string. Then modified will be set to 0 and apparently never changed again. Next is the gets function with our 64 character long char buffer. Let's have a look at the gets man page. So gets is used to read the string from the input. When we scroll down, we can also find a bug section which is telling us to never use gets. This cannot be more clear that this is the vulnerability in this program. As an explanation, it says that it's impossible to tell how many characters gets will read. It has been used to break computer security. And after the gets call, modified is compared to 0. If it's not 0, we have 1. But how can modified ever become non-zero? It's set to 0 and never changed. By the way, volatile is a way to tell the compiler that it should not optimize the usage of this variable. Because at first glance it looks like modified will always be 0 and thus it might simply remove the unnecessary if case. But with volatile we can force the compiler to keep it as it is. I think we have a good understanding of this program now in C. Let's open it with GDB and start debugging. First let's set a breakpoint in main with break main. Then type run or short R to start the program from the beginning. Now it's stopped at the start of main. With disassemble you can disassemble the current function, but also set the disassembly flavor to Intel because I like it more. Let's try to understand fully what is happening here. I ignored those parts in the reverse engineering introduction, but here we need the full understanding how the stack works. So let's start with the first instruction, push EBP. A quick flashback to my CPU introduction video. I mentioned that the stack is just a memory area at the bottom. And when we look at the mapped memory with info-prop mappings, we can see that the stack goes from BFFEB to Z00. And because the stack grows from the bottom, it starts at the highest address, so C0. But C0 doesn't belong to it anymore, so basically the stack starts at Z0 minus 8, which is BFF8. So push EBP. EBP is a register which is used as the base pointer, and it contains an address pointing somewhere into the stack. Okay, so whatever the meaning of this address is, it seems to be important because it gets pushed on the stack, which is like saving the value. And at the end of the main function, you find a leave. And the Intel instruction reference tells us that leave is just basically move ESP EBP and pop EBP. As you can see, the start and end of the function is symmetrical. At the start, we push EBP and move ESP into EBP, and when the function is done, we do the reverse. Don't worry, I will illustrate this nicely in a moment. Just one more little thing. After those two instructions, we mask ESP, which basically just sets the last 4 bits to 0 to keep it nicely aligned. Not that important. And then we subtract hex 60 from it. So ESP, the stack pointer, now points to a bit lower address than EBP. and the next instruction moves 0 at the memory location at offset hex 5c from the stack pointer. And that seems to be perfectly match our modified variable that gets set to 0. At first it's a lot to take in, but let's do it again, but this time with an animation. So here on the left you can see the assembler code, and on the right I will illustrate the stack with the 3 important registers: the instruction pointer EIP, the stack pointer ESP, and the base pointer EBP. So first it starts somewhere else with call main. Call will push the theoretically next instruction pointer onto the stack and then jump to our main function. As you can see, when the address of the next instruction was pushed, the stack pointer got incremented and the address is placed there. So now comes our push EBP. I will illustrate with some arrows that this value is a stack address which points to another location on the stack. Now we override EBP with the value from ESP. Move EBP ESP. Then we subtract hex 60 from ESP. Look at the stack now. This area between ESP and EBP is called a stack frame. This is now a small area of memory that we can use for local variables and calculations inside the main function. And do you notice where EBP is pointing to? It's pointing to the old EBP. So this area here is basically the stack frame of the previous function which called main. And we know that we move 0 into ESP plus hex 5c, which we think is the modified variable. And that's true. The local variables all have their space in the stack frame. And it's so big because it had to make space for at least 64 characters and the modified integer. At the end of this function, we will now perform a leave, which moves EBP into ESP, effectively destroying the previous stack frame. Then we pop EBP, which restores the previous stack frame. Isn't that amazing? Oh wait, it gets cooler. How do we know now where to return to from main? Well, if you remember, call pushed the address of the instruction after the call. So the next value on the stack is where you want to return to. And the red instruction is basically just popping this address into the instruction pointer, and thus jumping back where we came from. Computers, huh? Aren't they mind-blowing? So much smart stuff in there. Now let's continue with the assembler code. After value on the stack got set to 0, we prepare the EAX register with an address from the stack at offset 1c. LEA or LEA, load effective address, is similar to move, but instead of moving the content of a register offset into a register, it moves the address of a register offset into a register. And this address then gets placed on top of the stack. This is called calling convention. The programs and functions have to agree how to pass function parameters in assembler. In this case, the parameters are placed on the stack, and the gets function takes one parameter, which points to a character buffer, and the character buffer is on the stack. Thus we have to pass it the address where the character buffer starts. Afterwards, we read the value we previously set to 0, and with test we can check if it's 0 or not, and branch off to print one of the messages. So let's remove the breakpoints from main with del delete and set a breakpoint before and after the gets. Before we start, I want to show you a cool trick. We will define a hook that will execute some GDB commands when we stop at the breakpoint. To do this, type define hook stop, then info registers to show the register, and x24wx $ESP and x2i $EAP, and finish with end. This will now print the registers, the stack, and the next two instructions every time when we hit a breakpoint. Now continue and enter a couple of capital A's. Do you see those hex 4 ones? Those are all A's you have entered. Now let's see the content of the address. We check if it's 0. Simply examine ESP plus hex 5c. Still 0. But it shows us where it is located on the stack, and we look at our stack, we see that our A's are still a little bit too far away. So let's count how much we need. 4 characters here, then 4 times 4, that's 16 for a row, and we have 3 full rows, and with the next full row we can apparently write into those zeros. So run again, enter that many characters. I like to use recognizable patterns so I can clearly see which letter which row is. and looks promising. So a single step forward and it will load the modified variable from the stack into EAX. And indeed, those are the characters that we entered. Let's try this without GDB. We can use echo and our previous string and pipe it into the stack 0 program. Cool, it worked! Before we end, let me show you how we can make this input a bit more convenient thanks to Python. With Python-C, we can specify a command that should be executed. Then we can use print and Python's cool string syntax, which allows us to repeat this character multiple times. With this knowledge, you should be able to solve stack 1 and stack 2. It's pretty much the same task, just some different ways of input and a different vulnerable function. But if you invest some time, you can absolutely solve it. And I will not make a video about those. Next video will be about stack 3. This is when things start to get juicy. So, see you next time.